So welcome everybody to our roundtable on detector simulations, where we have three excellent speakers to come, each about an hour and a half. Formally, this is a 90-minute slot, but typically we go close to 2 hours. We'll see how this one goes. I'm sure there'll be interesting discussion. And we're going to start off with Sofia Vallecorsa talking about AI/ML for calorimeter simulations. Sofia has been doing work that we follow with interest in US Atlas, because AI/ML for calorimeter simulations is a key part of how we want to make HL/LHC computing manageable. And Sofia is a CERN physicist with a lot of experience in software development in high energy physics, PhD from the University of Geneva, working on the CDF, IceCube, Atlas, a real range there. She currently coordinates the quantum computing area of the Quantum Technology Initiative at CERN, and is also responsible for deep learning and quantum computing research within CERN. OpenLab, and prior to OpenLab time, she worked on the development of deep learning based technologies for detector simulation, code modernization projects in the field of Monte Carlo simulation with our old buddy Federico Carminati and others. So with that, Sofia, you can take it away. I'll drop the share.
Okay, thank you. I'll start sharing again.
And let me just mention that we have live notes. The link is on Indico, so please do contribute to the live notes, enter questions there for discussion later.
Okay, so well, first of all, I would like to thank you very much for inviting me at this meeting. I'll add a brief look at all the the topics in the past editions, and it looked like a very, very interesting gathering you're organizing here. As Tore mentioned, I've been working in this kind of application for quite some time. So I have tried to prepare for today as a sort of a review of some of the directions that characterize this field today. Of course, this review, I mean, probably you're used to this kind of caveats, but I need to say it anyway. This is my personal view of what's really interesting today, and it's absolutely not exhaustive in any way. I will use the few examples to try to point out what are the hot or important questions that are being answered and need to be answered today. And depending on how much time I'll have at the end, which is usually very little because I tend to run out of time, I've also tried to bring up some idea for future development. So let me start with just very briefly a word about deep generative models. You can see some examples there. If you look at the archive dates, those are very old for this time scale pictures, and I chose them on purpose because already at that time, so we're talking about 2016, 2017, the performance of those kind of models was impressive. Now, today, of course, the situation is even, it's much more improved. You're probably aware of those examples about pictures of people, synthetic pictures of fake people, which look very, very realistic. In general, deep generative models are successful because of that deep part that we see in the name. They exist as AI models, I would say, since tens and tens of years, but it's only after the large data sets became available and reasonable computing resources were also available for training that they really started to become interesting models and could achieve today's performance. They are used even in our field for many, many different applications. Those are multiplying every year. Simulation is one of the first that actually explored those models a long time ago. And also, as far as models are concerned, there have been a few generative adversarial networks in particular that have been used for quite some time, but the range is actually very large, and it's becoming larger now. So just to stress a little bit more this, I also wanted to show you, if you just go to Inspire HEP and try to find search for one of these keywords, you will find the large number of papers that are associated to that, at least the ones that are categorized in this repository, which are not all of them, of course. And if you specify the use of those kind of models for calorimeter, you still get tens and tens of papers, all clustered between the last few, let's say 5 years, or mostly clustered between the last 5 years. Now, this is very interesting because if you allow me a little bit of pride, to show a little bit of pride, we had started this discussion already in 2017. This was a presentation that I gave at ACAT, where we had introduced this idea of really using or integrating deep learning models within the structure of the simulation frameworks. Okay, so this was a very, very, if you think about it, it was a very simple idea, but very different from the approaches to simulation that were taken at that time. Now, of course, the founding, let's say, the seed papers for all of the works that started around those years and then followed is the Calogan model, which people continue to cite and continue to refer to this day. So it was a very, very important, I would say, milestone for anything that has to do with deep learning in our field, and of course, in particular for simulation. Now, going forward, I would say to today, let me just spend a little bit of time explaining to you how things are changing, in the sense that if you think about how our own model or the Calogan models were built at that time, those were relatively simple architectures that were able to reproduce simplified structures, simplified detector geometries. In the case of the Calogan, for example, there was this assumption that we could split the simulation of a calorimeter similar to the Atlas liquid arc calorimeter and use 3 two-dimensional images to reproduce its output, okay, which is what you see basically here. And the interesting thing is that even such a simple or simplified view of the problem actually led to very, very nice results. So we kept working, and I'll start with our model, but I will move away from it very quickly. We started from our initial prototype, which was called 3D GAN, because it used 3-dimensional convolutions to reproduce a volume of a regular grid of pixels in a calorimeter prototype. This is not a detector that exists. This is a detector studies that has been done for linear collider, in the context of the linear collider detector. The interesting thing about this kind of data sets is the high granularity, of course, of the pixel, of the sensor systems. So we had initially a very simple model, which amounted at less than 2 million parameters in total, taking into account the 2 networks that compose the generative adversarial network system. And we basically used this prototype to do a lot of different studies, from understanding performance in terms of accuracy and how well we could reproduce Monte Carlo output, to everything that has to do with understanding how computing resources can be optimized to do this kind of work. So we've recently, so I will not describe that. We've recently modified our model, embracing this I would say, not attitude, but let's say trend towards trying to optimize architectures a little more, moving away from very linear, if you want, approach architectures. And we managed to reproduce very, very good results by just by replacing our 3D convolutions with 2-dimensional convolutions, which has a big advantage of making the model much more lightweight, I would say, while keeping all of the accuracy that we had achieved with a much more compute-intensive 3D convolutions. And you see a few examples here where we compared the results for different physics features to 3D convolutions. So why am I showing this? I just wanted to, I wanted to highlight the fact that the study of the optimization of in terms of architecture that is used, that we choose to use, it's really important. And sometimes it's not necessarily, you know, the first straightforward approach that fits more, you know, right away with the kind of data set that we have at hand. Now, of course, this the situation, you know, more recent models have been introduced in the meantime, and I have a few examples here. So the first one I wanted to quote is Fast-Calogan, as Tore just mentioned. This is an interesting model. Per se, is not you know, a breakthrough architecture. It's a relatively simple GAN, but it's one of the first time, I think it's actually the first time, in which the full calorimeter detector can be simulated using a GAN. And the reason being that the authors decided to train a total of 300 networks, 300 GANs, in order to well, they basically sliced the detector in a certain number of voxels. They sliced the phase space, so the energy range in a set of bins, and they came up with a total of 300 GANs that are capable of describing the old detector for a large energy range for different types of particles. So it includes fast-Calo GANs, includes electrons, photons, pions. So this is it's kind of a brute force method, but you see it works very well. What's done is, I believe each one of the GANs is trained for more than 1 million epochs, which is a huge number. And then so the epochs that correspond to the best performance are chosen. And you see an example in the plot that I put there. There are also entirely different approaches that tend to focus more on, you know, introducing more complex architectures, trying to optimize a little bit the information flow within the structure, within the models themselves. You see another example in the second part of this slide. And I'm using here the idea of self-attention GAN. This has been introduced for the LHCb calorimeter, presented recently. I believe I linked their virtual chat contribution, but this was presented at different places actually. So in this case, the idea is to introduce within the GAN architecture self-attention modules. You see the structure here, which are the idea of self-attention layers is really that of optimizing the performance of the overall architecture on the local features that are highlighted by the model, right? And so this seems to work very, very well for a use case that at the end is similar to the one that we are all looking at. So very sparse images and very large pixel intensity ranges. In this work, in particular, the performance of the self-attention GAN is compared to one of the standard approaches that is an previous result that used Wasserstein formulation for the GAN in LHCb. I'm quoting this result also because of another reason, and I'll get back to it later, and it's the introduction of an interesting metric for evaluating the performance of generative models, but we'll get back to it later. I wanted to continue with this overview, if you want, of how architectures are getting more and more complex. I think this is something that is very, it's very interesting. It's also in line with the modern ideas, I would say, about deep learning. Deep learning is not simply building deeper models, so stacking together a lot of layers within our architectures, is really trying and optimize how the information flows happens through the complex computational graph. So this is something that you see here, for example, in this hybrid GAN autoencoder architecture, which was proposed by a group in Hamburg. It's interesting because, well, there are different things. Well, first of all, from the point of view of the performance, this model is capable of improving on a well-known problems of GAN prototypes. And it's the fact that the model is capable of reproducing very sharp edges. You can see this. So the architecture in question, so the architecture I'm describing is represented by the green line here. And you can see that it's the only architecture that is capable. It's compared to standard, vanilla GAN and to Wasserstein GAN. And you can clearly see how the sharp edge that is typical and clearly visible in Gen 4 is reproduced by this model. This is something that, for example, our own prototype did not manage to do, to accomplish. Again, also in this work, I think what's interesting is the introduction, the use within the loss function of, let's say, non-standard, I would say, loss formulation. It's not the only work that does that, but I wanted to highlight this as an important point anyway. Usually, vanilla GANs are built on the typical GAN loss with binary cross entropy loss that are used to incorporate the discriminator feedback. This is not necessarily or not anymore the only option or the best option for complex problems. The other example that I have in the slides is based on normalizing flows. And by the way, there has been just yesterday an HSF meeting dedicated to simulation in which more work on normalizing flows has been presented. So if you are interested in this specific architecture, maybe you'd like to go and have a look at what was presented. I have listed the agenda in the at the bottom of the page. So normalizing flows are models that have been introduced already. Well, the original formulation, I think, dates back to 2010, between 2010 and 2015, but their implementation as generative models is more recent. It's due to Danilo Risende, which is one of the biggest experts on generative models in general. The idea is that of approximating a probability distribution function, of transforming a probability distribution function into a more complex one by building a product of invertible functions. Okay, so this is very important. The invertible part is something that allows the formulation of a generative problem in terms of tractable PDFs and tractable loss function. The probability distributions are learned explicitly, which is completely different than what we do generally, for example, with GANs. And this not automatically, but this has the advantage of reducing the probability of having the presence of problems that are well known for GAN. Such as, for example, missing modes, so simulating data sets that are actually incomplete, or the opposite problem of mode collapse. The disadvantage is that this approach can be...
Zero is not peaking, it's just stacked on top of this, so it looks like it's peaking.
Yeah, okay. Can be expensive in terms of computation for training, okay? And there are solutions to this. And again, this was presented by the work that I linked here. This was addressed in the work that I linked here. So I hope those examples can show you that today deep learning based fast simulation is a reality. The number of projects and prototypes that are being developed in the different experiments is huge. I'm not even talking about also all the other applications beyond direct detector simulations, because there's actually many more directions within the field of simulation that are being explored, but I don't have time to talk about that now. I think what's happening, and this is very, very, exciting for people that have been working on this for some time, is seeing that there starts to be work to introduce these models to bring these models to production level and integrate them with simulation or fast simulation frameworks. So I mentioned before the FastCalGAN, that is part of the Atlas Fast3 framework. There is some work in the simulation group at CERN concerning the design of interfaces between GN4 to introduce, to call and use those tools within GN4. This is also very, very interesting. At the same time, of course, there has to be work that continues along the lines of, validation process. It should be somehow standardized. There are discussions also in this direction, and everything that has to do with evaluating computing resources, because at the end of the day, these all problems, it's very interesting per se, but it all started with the idea of solving the problems of the high requirement in terms of computing resources of the simulation software. I hope I can talk about generalization later on at the end of my talk, so I don't spend time now. Let me go through a few points that show you what I mean when I'm talking about those steps to production level deep learning. So the idea of validation, of introducing validation, not introducing, but of getting to a common set of validation metrics that we all agree on are useful and for evaluating and comparing different models and comparing those to full simulation tools. It's a complex topic, even more so because of the nature of generative models with respect to other deep learning problems. So the idea here is that we need to be able to measure the difference between the real PDF and the model, the one that the models learn. But the problem is that those models learn the PDF in different ways. As I said, GANs do this intrinsically. In other cases, it might be simpler if the PDFs are learned explicitly. There are different metrics that are proposed. Some of those come mostly from the field of computer visions and are being readapted to our own problems. I have here explicitly mentioned again the work that's ongoing in LHCb. They propose the use of this precision recall distribution AUC. So this is a methodology, a metric that was proposed for general. The original paper is linked below for the assessment of performance of generative models, and it's taking the idea of from accuracy models. So from classifications is slightly simpler. Of course, we can always rely on direct comparison between our physics distribution, the way we generate on GANs and Monte Carlo. But the problem is that there are, in addition, other aspects that can become relevant depending on the application we want to use those models for, okay? Depending how much we want to move away from a fast simulation, what are the constraints, what are the requirements for these data sets, okay? So, and I have listed a few here. Some things I've already mentioned. So the problem of monitoring mode collapse or mode dropping, of course, overfitting, but also things more related to the structure, to the properties of the event, of the synthetic event that we generate. So anything that has to do with saliency, an electron of a specific energy does look really like an electron with the same energy in GN4. This is something that we need to be able to answer. And also, what is the composition of our model? How well we can reproduce the support space. So some of this work has already happened. I wanted to get, I have a few examples for all the points I was mentioning, but maybe I could skip through most. I just wanted to mention this one, that using the example that we built, but this is actually an approach that has been used by many analyses recently. It's really the idea, and this is also taken somehow from the field of computer vision, of using a third independent tool to evaluate the quality of the synthetic data set. And I think this really makes sense, because what we can do is, what we are interested in at the end of the day is really understanding how the behavior of, I don't know, the reconstruction software, so all the subsequent steps in the data processing processing chain would apply to synthetic simulated data and to original Monte Carlo. Okay, so the idea comes from metrics such as the inception score or the Frechet inception distance, which are metrics that rely on networks that are used to classify the quality, to classify synthetic data. And so we can do the same with our GAN output in the case of detector simulation if we rely on tools that, for example, as the Triforce tools, which is the one we used for our data set, were developed and trained to do other tasks. For example, electron pion classification and energy regression. So we did look into this tool and we used it and we compared the performance on our GAN generated data and on the Gen4 data when we trained the tool on Gen4 and on GAN. And we checked the behavior of both tasks. And this was a very, very nice, I mean, it was very comforting for us to see that the tool didn't really see a big difference or any wasn't sensitive enough maybe, but its response to GAN and Gen4 events was completely compatible. And as I mentioned, this is actually a direction, a strategy that is being applied used by different tools. I believe also, again, if you go and look at the normalizing flows work, you will see that they have a very, very similar approach to model performance evaluation. There are, maybe just a word about systematic effects. This is generic, it's a generic problem that goes beyond generative models. There was some, so it's really about deep learning tools in general. So there was some work that I wanted to mention because it's been done by people, members of our community already some years ago. There was this interesting idea of teaching a classifier, of training as a classifier under the condition of systematic errors. So uncertainties on the probability distribution functions. And the network could automatically adjust its output, taking into account these uncertainty parameters that would be used in the training time. So I think this was very interesting. But of course, there is a lot more work that is already starting beyond the high energy physics field. I have more examples about data set size. I'm not sure, I think I'm running out of time, so I'm not going through all of those examples, but I just wanted to flash them briefly because then you can go and look at the work that was presented here. This was a nice small study that was done trying to understand how the size of the training data set could affect the level of precision that GAN events could achieve, that the GAN could achieve. And with surprising results. We can get back to this if you have questions. The idea of studying image similarity, I already mentioned this before. We also worked on some trying to understand how close to each other and how close to Gen4 our images are. So there are a set of metrics that you can use to study that. The idea of support size, this is a tricky issue, unfortunately. So the idea of how large, I'm trying and understand how large is the domain over which the probability distribution function are that the networks learn are defined. How large are they with respect to the original Monte Carlo PDFs? Support size, so we try to do this using a method that was originally proposed for images. We found that we concluded that probably this was not the best method to actually do this kind of studies for our use case. Well, this is the whole discussion about rare events. So how much are they, how important are they for our simulations? There are cases in which those events should be reproduced with with the correct, not only topology, but also with correct frequency. So the occurrence, how often they appear. This is another open question, but again, it might or might not be relevant depending on the kind of application. Okay, there is a discussion about computing resources, which probably I'm not going to go through, but I guess you are familiar and you have experience already on the fact that having a large cluster is probably best if we want to train, for example, 300 GANs, or if we want to optimize more complex models. So this is becoming more and more important in order to extend the range of applicability, but also the complexity of our models. And likely enough, it's becoming easier to get access to those resources through clouds or through dedicated accelerators, such as the TPU. You see an example here. But I wanted to get here before concluding. This is a test that we've done on applying reduced precision representation of our networks and measuring how much of the accuracy of the precision on our data set description we have, and what is the acceleration that we gain. So this is a benchmark that we run on one of the latest Intel architectures, and you can see here we show the showers per second, so the throughput of our network, which is very, very high. So it starts to get to the level of almost 8,000 images with intake precision, so with reduced precision on a single node, which is a huge number. Now, of course, this looks like a number that is very, very difficult to achieve with a classical Monte Carlo. We can't forget and I didn't want to make direct comparison here. We can't forget what it takes to actually do pre and post processing of those kind of models. So what I wanted to stress is the fact that if we really want to gain or to profit fully from the speed up we can achieve using those models, we need to be smart about the way we integrate them in our simulation frameworks. And before concluding, this is where I really wanted to get, and it's the idea of some ideas for further development. I had the chance to follow this keynote. This is already not so recent anymore, but this was a keynote for the Tuning Award winners event at the AAA conference, which was given by Hinton, Lecan, and Benja recently, about new directions for deep learning. And what I really stress is the fact that while the origin of these approaches lies in the study of human brain, today most of the architectures and methodologies that we use bring the artificial learning process very far away from the way humans actually do that. So there is the research today on deep learning is really trying to improve this aspect. And it's from this perspective that a lot of those new techniques in terms of training and learning, for example, few shots learning or self-supervised learning or meta learnings are born. Generalization is the other important aspect, and I think it's very relevant if we are talking about simulation. The idea is, and I'm getting to the last slide basically. So the idea is that we probably would like to move away from the situation at some point, from the situation in which we need a new prototype every time we want to simulate a new detector. Now, there is this idea already quite developed for other problems and for other fields, and in particular, everything that has to do with natural language processing, where those huge models originally started, about foundation models. The GPT-3 model, I don't know if you're familiar with it, it's a model with 175 billion parameters, is one such model in the sense that it was trained on a huge data set, the whole of internet probably, and it's then specified or specialized in order to perform at best multiple downstream tasks. So this is an approach that is very, very interesting and probably relevant. This is connected to what I mentioned before about meta learning. So the idea of, instead of learning data distribution, we want to teach the networks to do tasks, okay? Maybe we should start thinking about the possibility of using this approach for our simulation problems. This is not the exact same formulation, but I think it's an interesting direction enough to actually raise some, some questions about it. So thanks. I'm sorry, I see I'm late. This is a summary, but it's just repeating what I just told you. So we will skip it and get to the thanks slide.
Thank you very much, Sofia, for that excellent and up-to-the-minute survey about which we could talk for a long time. But let's take a few questions. Let's see. Maxine, you want to go ahead with your question?
Yeah, thank you. Thank you for this excellent presentation. I have a rather pedestrian question. You described many interesting, efforts. Is there a common pattern as to how you interface your domain software with the machine learning machinery? Do you compile it and build it with your application? Do you export it and then do Python, TensorFlow? What do people usually do to interface their specific experiment software with the machine learning? Thank you.
Okay. So what is happening at least at the R&D level today is that most of those use cases are developing those the models independently. So it's a completely outside the simulation or the detector, the experiments software. But at the same time, so it's kind of, the process goes the other way around. We do the prototyping outside, and then we are trying to bring it in and interface it with the frameworks. What happens, the solutions that are being used, not only for simulation, but also for using other deep learning for other tasks, such as reconstruction, classification, triggers, a lot of those, the problem of integration is common, right? So it's both. What you have the option of actually compiling those models into libraries, for example, C++ libraries, and then link them directly to the experiment software. I know there are different libraries or tools to do that. I believe one was also developed in the context of the Atlas experiment, but that I might be wrong. So I don't want to quote names to avoid problems, but I can search it if you're interested on that. The other idea is to also export those models into common format like the ONNX format that then can be read in by different libraries. And we shouldn't forget also, because we are talking about simulation Gen 4, that there is the root option. With TMVA is capable of reading in models that are developed and defined with different deep learning framework, from PyTorch to TensorFlow and others, I believe.
Okay, let's do 2 more quick questions. We have 2 hands raised, so you guys get priority. Marcus.
I would like to point that David Lawrence and Cristiano Fanelli put 2 questions in our live notes.
Oh, thank you for following that. Okay. So why don't you've got it in front of you. Did you have a question of your own, or you were pointing that out?
I'm pointing this out. I also have a question on my own, but I prefer to go last just to let everyone else go. So David, would you like to ask your question, or should I read it on your behalf?
Well, she could probably answer that offline. It was really just
I can do that if you want.
Sure. For the sake of time. Yeah.
Then we go to Cristiano. Should I read it, or would you like to give your question?
No, I feel I have to read it. Thanks, Marcus, because the way it's written here is sort of a comment / question, because I think it is really interesting to hear the developments on validation with external tools, and Sofia brought up the examples also from LHCb. But one thing that might happen is that you might have observed different performance in comparing, right? Your simulated data, your synthetic data with your Gen4 simulation, depending on the different external tool that you're using.
Yes.
And there might be some systematic differences. And therefore, I think this should be taken into account somehow in characterizing essentially this with external tools.
I certainly agree. Now, those are more like demonstration kind of tests. What would be ideal, I think, is to, be able to use the real, whatever real, next step is running the experiment. Okay, assuming, for example, we are reproducing calorimeter, we are simulating calorimeter cells. It would be great to run the, jet clustering algorithms on those cells and then see whether we find a difference, right? But this needs to be done, once we are able indeed to interface back or to read back our, let's say, GAN or network simulated events in the experiments workflow. But I agree, it's a good point.
Okay, Marcus, do you have a quick question of your own?
Yes, my question is, you had the slide where you linked that keynote regarding how humans do learning and how we use deep learning, and you emphasized on the fact going really into the direction of artificial intelligence. But to what extent do you really see this necessary for our field? Because what we are used to doing is working with mathematical methods or mathematical models, and mathematical modeling is not necessarily something is how our brain works. So how do you see this coming into our field?
So for me, I mean, maybe I should indeed have show the summary slide. So I think, of course, at this point, the accent and the most of the efforts should be put into other things. So full integration, as I stress here, because there has been a lot of enthusiasm about those introducing these networks, these models, and there has been a lot of research. But they really do make a difference if they are integrated in the experiments. Now, that said, the idea of following up on those approach and this direction of research can be a huge opportunity for us to improve on the models we already have, because the research is moving fast. So I'm not so much making here a discussion about what is the best approach for this, but more like it's kind of an opportunistic view. I think we can learn a lot from that, even if it's an approach that is very different from what we are used to. And I think this already happened in the past when these models were first introduced, or we started looking to them. And I think it can happen now if we continue, keeping an eye and maybe on the side, at least for some people, keep track and keep experimenting with the new technologies. Even though priority for me is to be given to integrating this into the way the experiments work, because it's worth doing it at this point. I'm happy to see there are already initiatives in this direction.
Okay, Doug, you've been patient with your hand raised. You have a quick question.
Yeah, on slide 19, you talk about reducing the training time. And these all seem to be data parallel.
Yes.
Is that really where we continue to go, as opposed to shared memory across multiple?
No, not necessarily, or at least not for very big models. I didn't stop on this slide, but I put it there just to show you the trend. So you can see here that researchers at Microsoft Azure were able to train trillion parameters models by building hybrid strategies for distributed training. So both shared memory models model parallelism and data parallelism combined all together. And this, I believe, it's not necessarily needed today for most of the models we are using, but it's key if, again, we want to move in the direction of more, generalizable or generic models. So this is certainly a very good point.
Yeah, I wanted to ask you how important large-scale resources are, but you answered that nicely. Thank you. So we really have to move on. I just want to say, Makoto, we will go past noon Eastern if we have to give your talk and the discussion around it. Fair treatment. So now we're on to the second talk. Cristiano Fanelli is going to tell us about AI/ML for detector optimization. Cristiano got his PhD at University of Rome. He's a research scientist at MIT, associated with the Lab for Nuclear Science and the AI Institute there, an experimental nuclear physicist working on hadronic physics, who's been working at JLab, Compton scattering, I think in Hall A, GLUX in Hall B. He's working on AI and detector design that he's going to tell us about, development of reconstruction and particle ID algorithms for Cherenkov detectors, for example, and involved in recent years on the design of the EIC. And co-convener of the computing team of ETCHI. And it's been very interesting to see how in the context of ETCHI and the EIC, in general, he's been a leader in giving early treatment to applying AI/ML and notably to detector optimization that he's going to talk about today. So Cristiano, you can take it away.
Thank you, Tori, for the introduction and for inviting me here at the Software Computer Roundtable. As the title suggests, I'll talk about detector optimization, and it's correct. I will bring some examples for EAC. One thing I want to mention is the recent workshop that we had at EAC. So the first workshop on artificial intelligence for EAC, because some of the slides I'm showing are essentially inspired to discussions and results that have been presented there. And there is a website, which is eac.ai, and we had different sessions. One of these was for AI for design. And so essentially, this is what I'm going to cover more or less in this talk. So without further ado, when we talk about AI for design, so this is a relatively new but active area of research across many fields. There are many applications. Most of them in fields like industrial material, molecular and drug design. On left and right, you can see a table and you can see some figures. On the left, you can see different machine learning methods and their corresponding applications. And again, the domain, you might spot some of the words, but essentially those I've mentioned. On the right, you may see direct and inverse design. This is another trend in design with artificial intelligence, with the idea that one can start after the learning process directly from the co-design, the co-domain of your design problem. That is from your desired properties back to your design space to identify what is the corresponding design that satisfy those requirements. But the bottom line is that these techniques, they typically require large data sets to produce these data points. And when it comes to AI for experimental design, I would say in both nuclear physics and high energy physics, we all know that we need advanced simulations and utilization of platforms like GIANT, which might be computationally intensive. And also in optimizing our designs, we do deal often with non-differentiable terms. Like, for example, when we have to take into account mechanical constraints in a dynamical way during the optimization process, we also have noisy functions. You can think of figures of merit characterizing your physics, and they might have noise. And all in all, in this context, we want to reduce the computing budget in doing this optimization of the design. So one comment here is that in general, the full detector design, and this is independent on AI, is studied once the subsystems, so the subdetector prototypes, if you want, are ready. And in characterizing each subdetector prototype, what happens usually is that we take into account constraints from the full detector, or if you want, the outer layers surrounding that subdetector. And when every subdetector is ready, then we combine essentially the subdetectors together. So this has been done, I would say, usually and in the past. But now when it comes to designing detectors with AI, this is an area at its infancy. I think it's a fair statement. We do cope with complex detector designs in facilities like, for example, EAC, and we have many parameters characterizing our designs, and we might have multiple objective functions. So objective functions here is another way to say, if you want, a driving criteria, or if you want, figures of merit that drive our design. And in a multidimensional space for your design, and also in your codomain for the objectives, well, we might incur in what is called the curse of dimensionality very easily. And what happens is that when we design complex detectors like this, this entails incorporating a complex body of instructions, like, for example, complex parameterization, but also how to take into account constraints. And also it entails some degree of customization. Because the reason is relatively easy to understand. I mean, the choice of a suitable algorithm, it's a challenge itself. And there is no free lunch theorem. We already know that. And therefore, at the end of the day, it's very easy to end up with some customization, some degree of customization in your optimization problem. In this context, AI offers state-of-the-art solution to solve complex optimization problems. I will try to provide some examples. But clearly, this is an opportunity, especially nowadays, for new experiments, which are in their design and R&D phase, like the electron-ion collider. So the electron-ion collider, there is probably no need to go into detail. I think everyone knows, or at least have heard of the EAC nowadays. It will be built in 10 years from now, approximately, at Brookhaven. And it is a collider that will collide, of course, electron and ions, beams, polarized. There are two possible detector locations. And at the moment, there is a competition among three proto collaborations, Athena, Core, and Ecce, that are working on a detector proposal with a deadline, which is December the 1st. But this year has been really active and hectic, I would say, in developing this detector proposal. The physics goals, well, it's actually a multifaceted experiment, and a lot of physics can be done out of EAC. The findings from the National Academy of Sciences was that EAC can address problems like the mass of the nucleon, how it arises, or try to provide a comprehensive picture of the spin of the nucleon, and therefore trying to solve the spin puzzle. And also try to shed light on the emergent properties of dense systems of gluons. So this is a machine that will have high luminosity, and it will cover a wide range in center of mass energy. And ultimately, we do need to provide an hermetic detector, which has almost a 4 pi coverage in phase space. And for an experiment that we will build in 10 years from now, it's quite remarkable that we have an increasing growth in terms of the numbers of active EAC users. As you can see here, we reach almost 1400s, and probably already went above that. And you can see also how this is spread worldwide. So it's a global effort. Now, this is a oversimplified overview of an example for the EAC central detector. The EAC central detector is essentially made by 3 main parts. The barrel in the central region, and then we have 2 end caps, one in the electron going direction called the end cap, and the other one electron end cap, and the other one hadron end cap on your right. The different colors here and the color legend highlights like in a layered onion-like structure, starting from the interaction point, what are the main ingredients in this detector design. So we have a tracking, an inner tracker, but we also have outer tracking stations. And then green is essentially the particle ID. Particle ID, the backbone of PID in EAC, is essentially provided by imaging Cherenkov detectors. And then we have, in red, in all directions, we have the electromagnetic calorimetry, and eventually in blue, the hadron calorimetry. What I'm going to talk about in the next slide are two examples. One in the hadron going direction, which is the dual rich. So this is one of the detectors for PID in the hadron end cap. And then I will talk about the inner tracker from HEP. So a general workflow for detector optimization is depicted in this slide. So typically what we do, we inject physics events into some detector simulation, which is characterized by design parameters. And then we want to get physics out of it. So we analyze high-level reconstructed events. This, in turn, can be injected back into some artificial intelligence. So this is some algorithm, some architecture that you have that collects information and suggests what are the most interesting points to query at the next iteration. So this is a sequential approach. And so you have your design parameters, new design parameters, and then these proceed in a sequential way. Now, why bothering with AI at this stage, in particular for the detector proposal that is happening and that happened across 2021? One common misconception, I would say, is that optimization does not really mean necessarily fine-tuning. There are at least two steps. A first step is steering the design. And what I mean with that is that AI and let's say optimization with AI suggests parameters that otherwise a manual or a brute force approach will likely miss to identify. And then there can be actually a second step where you can further optimize things and maybe fine tune. But all in all, I think one important point is that AI in a combinatorial problem outperforms and allows to capture hidden correlations among the design parameters that otherwise we will miss. And as we saw in the previous optimization workflow, all steps are included, meaning physics, detector simulation, and AI on top of that. But this reflects also in the way actually AI fosters, promotes an interplay between the different groups. So physics working groups, detector working groups, and computing working groups. And AI is assisting essentially in this process of providing a better design, as I will try to explain in the next slides. Now, one of the most popular frameworks for optimization is certainly Bayesian optimization, which gained in popularity in the last few years. It is a principal sequential approach. And this oversimplified picture here represent in two instances of time what happens, essentially, the mechanism of Bayesian optimization. And oversimplified because we have just one dimensional problem. So one parameters for design, and we also have one objective. And therefore you have a time Tn, 3 observations. And you want to build a posterior that represents your objective function, which is unknown. You don't know it analytically, based off these observations. And of course, what happens is that here in between these 2 points, you don't have information, and therefore you have the larger uncertainty. And what happens here, and this is one of the smart features of Bayesian optimization, is that you can have what is called an acquisition function. That is a computationally cheap function that reads your posterior, your surrogate model, and suggests what is the most interesting point to query at the next iteration. And therefore, at time t n+1, what happens is that the most interesting point is here. And you gather this observation, you update your model, you see an improvement, and then, of course, you update your acquisition function. And this can go on in a sequential way. And things, of course, are always more complicated than in theory.
Why? I mean, I
And as you can see, I will try to continue. So this is the actual implementation that was under the hood of the optimization of the dual reach. And you can probably immediately realize that there is some parallelization. So different design points have been parallelized. And also there is control on the convergence in the AI part. What is nice is that you can have a visualization in terms of your parameters space, design parameter space of the dependence of your objectives. And therefore you can understand every hidden correlation in this way. I will go into more details in the next slides. And also it's very nice that you might have control on both the design and the codomain, which is the objective space for controlling the convergence. So all in all, this has been the first AI paper in EAC, utilizing specifically AI-based approaches for optimization. And when we were leading these efforts, essentially what we had in mind was the dual reach, of course. Why the dual reach? So the dual reach, first of all, as the name suggests, is made by two radiators. It's an imaging Cherenkov detectors. Two radiators, aerogel and gas. The reason for that, two different refractive indices. And this allows essentially to have a large coverage in momentum of the particles to do particle ID. And you can appreciate probably in this figure that there is some modularity in the design, and we have 6 petals here that repeat. And we also have a large mirror that reflects the Cherenkov light produced by the passage of particles through these two radiators back into these 6 tiles of detecting tiles. And this was one important point is that we inherit a baseline design. And we want to optimize that design. And this design has been studied by INFN. Back in the day, it was 2017. And we start from there. And so we already had knowledge and we encode this knowledge in the optimization problem. So essentially in this table, you have mainly geometrical parameters characterizing, for example, the radius of the bigger mirror or the position of the tiles, but also optical parameters, like for example, for the aerogel radiator. And you have ranges for all of these parameters. And ranges, they mainly depend on constraints or optics requirements that we knew from the studies from the legacy design from INFN. Also construction tolerance. The construction tolerance, the meaning of this is that variations below these values are irrelevant. So you want to provide a design point that is consistent with the construction tolerances. So all in all, we encoded this information, and you have to build some figure of merit, which is your driving criteria for your design. And the most natural choice, in particular, if you tackle the problem with the pion and kaon separation, which is probably the most challenging one, is choosing the separation power. And a proxy for that is the number of sigmas that you can obtain, which is calculated or defined as the difference between the average Cherenkov angles under the true hypothesis for pions and kaons divided by, if you want, the resolution for the single photon. Now, if you remember, there are two radiators, and therefore we characterize the very same figure of merit for two different points in momentum, so different momentum values. And we made an harmonic mean of the two. And you can see how the separation power evolved as a function of the number of calls. So this is zoomed in, the same picture I showed before. And you can see how the surrogate model evolved. Actually, more details here. So this is a pairwise representation as a function of all the parameters of the surrogate model. And the points from white to black, they are the actual observations calculated with our simulations. From beginning to the very end, which is black. So there is a gradient in color. And the surrogate model is the snapshot at the very last observation. So it's the last update on the surrogate model. And on top of that, there is a diagonal with the partial dependencies. And the partial dependence provides information on essentially the dependence on each parameter for your objective. So all in all, we got all this information together and we were able to optimize starting from these dashed lines for the pion and kaon separation as a function of the momentum to the continuous solid lines, blue and red in the two regions for the dual radiator. You can see that there is a statistically significant improvement, probably not visible here. There are also statistical uncertainties in these curves. And also notice that before starting this study, we did not know how well the legacy design was performing. So in principle, if you end up with something that is consistent with the legacy curves, doesn't mean that AI didn't improve or didn't optimize anything, but perhaps you were already sitting in a global optimum. So this was the achievement. And typically what you want to do, you also want to benchmark against some other method, and the most natural choice is random search. So what happens is that even with a relatively simple, simplified, let's say, problem with 10-ish dimensional parameter space, you can easily realize that random search, despite being embarrassingly parallelizable, doesn't perform well. Meaning that you can see that essentially the figure of merit in red is the random search as a function of number of observation. It's far away from what we can obtain with Bayesian optimization. And on the right, you can see the time that it takes, and essentially at the same time, we are really far away from using 20 cores. Actually, we made studies with 50 cores. And I think we also tried to do that, to characterize that with 100 cores. There was no way essentially to perform as Bayesian optimization. But one interesting thing, sometimes is always useful to look back at the old literature. So Benjo, in this paper, he highlighted how random search can be actually effective if the interesting region for your solutions, depicted here with this small v, so if the relative ratio of this volume, interesting volume, compared to the overall explore volume, if it's large enough, then random search becomes effective through this empirical formula, which makes sense. So for what we explored, that was not really feasible and not really doable. So now I want to provide another example, which is the HE tracker. So the HE tracker is essentially depicted here, but for the sake of truth, this is a snapshot of a few months ago. Things kept evolving. And highlighted here in yellow with this dashed rectangle, you have essentially the inner tracker highlighted. And the inner tracker in particular is of interest here because we utilize AI to optimize it, but we took into account the whole tracker system, also without the tracking system in doing that, in characterizing its performance during the optimization process. On top, you can see, of course, this depicted as a function of the pseudo-rapidity or the polar angular momentum, if you're more familiar with that. And in the inner tracker, we have essentially silicon technology, so silicon layers in the barrel, as you might see, and in the two end caps, we have silicon disks. You can see also some different technologies in the outer tracking layers. So in this regard, in our study, the geometrical parameters characterizing the location of these silicon layers and the silicon disks had significant impact in the performance of the tracker. We need an effective parameterization of the detector design. So most of the work has been done on this aspect in particular. And actually, it's really useful also to come up with a clever parameterization that allows also to reduce dimensionality. And we also need to encode different geometrical and structural constraints. For example, the ITS3 technology, which is the silicon technology in ALICE also, carries fixed strip length in the problem. So you have to take into account these constraints and other mechanical constraints in a dynamical way. And also now shifting to the objective space, design is characterized by multiple figures of merit. For example, resolution, reconstruction efficiency of the tracks. And so analysis have been done considering simultaneously multiple tasks. One thing I want to mention is that not depicted here, but just highlighted separately, we also have, just for clarity, we have a support structure that has been parameterized as well, because of course these elements cannot float, right, in a simulation. So reality, most of the time, is made by multiple objective optimization problems. Allow me to be a little bit faster in pace in the interest of time, because we have another talk later. But when we talk about multiple objective optimization, we talk about optimizing and getting the Pareto front. So for example, in this simplified scheme, if you have two objectives and you want to minimize both of them, then you want to approximate the Pareto front. So you might start with some design point, which has these values of F1 and F2, point C, but you can see that A and B are better than C. They belong to this trade-off solutions. This is a set of trade-off solutions. And A with respect to B, well, it performs better in F2 because it has a lower F2, and B vice versa for F1. So multi-objective based solutions are helping to reveal important hidden knowledge about the problem, particularly in the design problems. And in the H-inner tracker design, we optimize momentum, angular resolutions, and Kalman filter efficiency. We also extended this to pointing resolution, and we consider mechanical constraints. And you have to come up also with some visualization, like, for example, petal diagrams. And typically, what you will see in the next slides is something that utilize a ratio. So it is essentially the performance evaluated for the new optimal design as it is evolving with respect to normalize to the baseline design, some baseline design you start from. And so the name of the game is obtaining ratios that are below 1, which means an improvement. And here for the Kalman filtering efficiency, the name of the game is going as close as possible to 0, because we are using an absolute value for the Kalman filtering efficiency. So multiple objective optimization. Nowadays we are lucky. There's plenty of frameworks. There has been a growth, I would say an explosion of applications in the last few years, especially on multiple objective optimization within a Bayesian framework. I would say, though, that dynamic evolutionary algorithms are the most explored and the most utilized so far nowadays, and I'm going to talk about those. Agent-based approaches are also possible. I'm not going to discuss about it, but remarkably, all of these approaches can accommodate mechanical and geometrical constraints during the optimization process, which is something that is really useful. The algorithm that has been implemented is what is called the elitist non-dominated sorting genetic algorithm. At the heart of this, there is a genetic algorithm. And you can see names like crossover and mutation operators that characterize the genetic nature of the algorithm. And this is used to create, starting from a population of n design points, to create an offspring of new design points. But then you have to sort them. So you want to approximate the Pareto front, and you will have different degrees of approximation, if you want, of the Pareto fronts. But then you need to trim some of the solutions, because you want to get back to the initial size of the population and update that at time t+1. And so you can use a metric. One of the most popular is called crowding distance sorting. And under the hood, without going into details, you can imagine that the objectives we are using are actually evaluated in very tiny, small bins in pseudo rapidity and in momentum. So we extract these functions, the fit functions and the values from that. And then we build overall these ratios, meaning objectives calculated for the new designs normalized to the baseline design. And all in all, we have to combine this information. And so you can see, you might see here a weighted mean. And of course, this weight propagate uncertainties from all the fitting that we do. And this is done for momentum and angular resolutions. For the Kalman filtering efficiency, the definition is a global quantity. So it's the badly reconstructed tracks normalized to the total number of tracks. And the software stack, it has 2 levels of parallelization. So we parallelize the design points. So each design point is parallelized. And the second level of parallelization is indeed that each design point is parallelized. And also the addressing and studying, characterizing the time performance of both the simulation and the AI algorithm is very important. And we have done studies here And all these, there is work ongoing in completing this, actually implementing in Dask for the distributing the two-level parallelization. And you can see also here for the AI studies, for the timing part, you can see studies that have done also independently using some test problems like DTDLZ1 as a function of the population size. But all in all, it turned out that for the complexity we are coping with 11 variables, we cope with different problems actually, but let's say 11 variables to have a reference and 3 objectives. We are talking about, for steering the design, something like 10,000 CPU hours. And of course, complexity can increase and you might want to approximate the Pareto font more accurately. And in that case, you might want to increase your population size. So all these things have been taken into account. So another nice thing that I want to highlight, well, first of all, this is an unprecedented attempt in detector design for complexity, even if it's a starting point to some extent. And a nice feature I like to highlight is that during the optimization process, you can take snapshots of your approximated Pareto front. So for example, here, you can imagine to have a Pareto front, remember, made by different solutions. Each solution here represented by a petal diagram with your objectives, but actually each petal diagram corresponds to one design, and each design is characterized by the objectives, which can be evaluated as a function of the phase space. For example, here you have the Kalman filtering efficiency as a function of pseudo-rapidity and generated momenta. I won't go into the details. And then momentum resolution and angular resolution. And you can see on the bottom the ratio with respect to the baseline design for the very same objectives. And you can see the improvement. How do we validate? Well, you can take other objectives, other figures of merit that do not enter into the optimization process. And you can see, for example, the reconstruction efficiency that is calculated post-hoc. And you can see actually that blue that comes from AI, it improves with respect to black. And as for the decision-making process, this is left post-hoc, and this is done on purpose. Why? Because at the end of the day, so if you want, this is a starting snapshot for a sequential process. So what happens is that you might have different technology choices, and you want to develop different optimization pipelines. And then you have this interplay, as discussed before, among the different working groups in your collaboration. And then you bring up your results from AI. So AI is assisting, is providing insight in the performance of your detector, giving a technology choice. And then what happens is that, well, in the optimization process, you might come up with new ideas and you might come up with alternative configurations based off of what you learned. And therefore, you might have new optimization pipelines that you want to run. And not only design, but also R&D. Another thing is that these techniques can be utilized, for example, to characterize aerogel material. This is another project. We are reinforcing aerogel because it's severely fragile with fibers. And so we are essentially coping with an optimization problem that has both the resolution of the Cherenkov angles, but also the stability of our tiles. I want to conclude by saying that if you have larger data sets, then of course you can think of learning, maybe with some deep learning, right? The mapping between design parameters and objectives, which is all it matters eventually, but you need to have large data sets. And this is not trivial. And of course, you can imagine to do, more or less fancy things we have seen from Sofia before, for example, also, on flow-based models, maybe inverse designs. But another consideration to make in terms of fast simulation within an optimization pipeline, there are a lot of speculations in terms of end-to-end optimization pipelines, embedding a lot of, for example, deep learning. But one of the tricky aspects is that you need to have information as a function of the design parameters. So you have to change and you have to produce your data, and then you have to learn to inject that to some architecture. Thing that is not trivial. Plus you may have, non-differential terms, and so maybe hard to achieve. In summary, ESE can be one of the first experiments to systematically leverage on AI during the R&D and design phase. HE create an AI working group, so we had a workforce to lead these efforts. No one ever accomplished a multidimensional, multi-objective optimization combining multiple subdetectors together. So parameterizing all of them and optimizing all of them together. Of course, things can be extended to include things like costs, speed up bottlenecks. I already mentioned about larger population for improving accuracy. A recent trend is distributing MOO in supercomputers. And this can be utilized in several fields, like, for example, medical imaging. I want to say on the right that these are two snapshots taken on June 2021 and August 2021. And you can see that red to green is essentially from baseline to optimal with AI. And then another snapshot, black to blue, again, utilizing AI, and you see the improvement with blue for a given pseudo-rapidity bin. And I want to conclude by quoting the conclusions from the DOE town halls on AI for science. AI techniques that can optimize the design of complex, large-scale experiments have the potential to revolutionize the way experimental nuclear physics is currently done. Thank you very much, and apologize for a few minutes late. Thanks.
Thank you very much, Cristiano. Fascinating and very impressive. In the absence of raised hands, let me ask one. You mentioned cost. How do you manage constraining the costs so your optimization doesn't build you a detector that you can't afford? Is it implicit in the constraints that you do have? And maybe a related question is, are you not optimizing characteristics of the digitization, like readout granularity and such?
Right. So in terms of the first question, so this is one of the most one of the most challenging aspects is having a reliable parameterization for costs. And this is almost independent on AI, if you think about it, because it's really difficult to parameterize costs as a function of your design parameters. But if you have such a function, then parameterization, then you can include in your optimization. Now, the question can be read in a slightly different way. That is how you take into account the constraints of the costs. So how you do not exceed those, right? So I think in the first instance, you encode your information, and maybe you have other constraints like geometrical constraints that you take into account in such a way that you are not exploring. Like, for example, I'm using surfaces as a proxy for cost, okay, which we know it's not all it goes in costs, right, into costs. But you can do these considerations and you can utilize that in such a way that you do not end up in something that you know is not feasible cost-wise. Right, and the other question, sorry, Tori, can you please repeat?
Digitization, like
digitization,
granularity, right, which would blow up the cost really fast.
Right. So, of course, in your simulations, you try to encode all the most realistic simulations that you have, which might include also digitization. So you can do approximation, of course, but I don't see it as something that is really, I see it more as a problem in providing a realistic simulation per se. So, for example, what we have done for the dual reach, we consider essentially performance related to multi-anode PMTs, right, for the tiles. So this is something that has been done, but that was back in the day the most realistic simulation we could provide, and this, of course, goes, you know, with the simulation that you are providing and the problem you are coping with. Which might be related to other considerations, like, for example, also the magnetic field of your detector. So.
Okay, thanks. I see Sofia has a question.
Yeah, I mean, I don't know if you want, I can also write it in the live notes if you want to go ahead as you prefer.
Oh, go ahead. We're going to go past, I think I said we were going to go past.
Okay, so quickly. So while this was very nice presentation, a very interesting application, I think it's extremely important. I was just a little bit confused because in slide 11, you show in the architecture, the overall framework architecture, and you mentioned optimization, machine learning, deep learning approaches, but then at the end, yes, here MLDL reinforcement learning as you know, help or, you know, tools for optimization. But then in slide 28, you write that you can't actually do that right now. So basically at this moment in time, the optimization happens through Bayesian optimization and Pareto optimization, depending on the use case. But there is no real learnable system in there, right?
No, thanks for bringing this up because it allows me to clarify. No, so in the previous slide, I was referring to the regression part. Because when you have a Bayesian framework, right, you need to do some regression to provide a surrogate model. And so you can do that with machine learning, deep learning.
Okay.
Right?
So that's you're doing
we
that.
definitely use machine learning and deep learning.
Okay.
What I am more skeptical about is, for example, embedding fast simulation within a detector design optimization. So while I'm a strong advocate for fast simulations to speed up bottlenecks that we have in our simulations, I think it's much trickier. I'm not saying it's impossible, but it's more difficult to embed this within an end-to-end detector design optimization. The reason for that is because you have to learn how essentially your fast simulation changes as a function of the design parameters. And typically, the fast simulation that we do study, and you have provided very nice examples before, they are characterized as a function of, for example, kinematics, right? For reconstruction, but you have to augment you have to extend your space to include also the design parameters. And this means that you really need to have a very large data set to do that. And also you have to take into account that solving one of these bottlenecks may be not the ultimate answer in solving the overall detector response that you might have, because at the end of the day, you have different pieces in this overall pipeline, because you're considering all steps together in the detector optimization.
Yeah, no, but I was referring more to the use of AI as here in the top of your slide, rather than AI for fast simulation instead of detector full sim. So it was a different question. It was really like the use of AI as the tool for guiding instead of simple Bayesian optimization, basically. That was what I was referring to. But maybe I can specify this better. We can follow up this discussion.
Oh, no, well, so I'm not sure what is meant by easy, basic Bayesian optimization. So multi-objective optimization problems are actually cutting edge problems.
No, that's not what I.
And also machine learning enters in the regression part, as I explained before. And here, for the other, I also talk about genetic algorithms essentially.
Yes.
And that is in the literature AI, right? So
yeah, and that's why I mean my question is really in this context. So this upper part of your slide where you say AI gathers observation and suggests new point. So you do implement some of it using, for example, genetic algorithm to solve the multi-objective optimization problem. But you don't, so the point you want to make here, and so the lack of large data sets and things like that is referred to alternative, for example, to this approach. Did I understand this correctly? So the fact of, for example, using reinforcement learning to drive the same kind of design instead of using multi-objective optimization based on genetic algorithms.
You can use reinforcement learning to achieve the same goal.
Okay, so there is no restriction actually. As soon as we have relatively reasonable data.
No. As I said at the very beginning, I think what did I say that actually? So there is always some well, there is no free lunch, right? and you can utilize different approaches. And actually, there's one slide, I think it's this one, where you might see also reinforcement learning. So multi-objective reinforcement learning and policy adaptation. So
okay,
We're really gonna move on.
Thanks.
Doug, is it very quick? You raise your hand.
Yeah, you can stay on this slide. The mechanical and geometric constraints are essentially, can you build it? And that gets folded into these frameworks now. Is that correct?
it is.
Perfect.
Okay, concise answer. Thanks. Thank you very much, Cristiano. So I hope everyone can stay past the hour, and in particular, I hope Makoto can stay past the hour to give him in due time for his talk and the discussion around it. Makoto, can you stay past the hour, 1 p.m. Eastern?
I haven't had breakfast yet, but I'm okay.
Okay, well, if you're willing to starve a bit longer, I hope you and ideally everybody can stay past the hour so that we can proceed with Makoto, who really needs no introduction, but nonetheless, I will give him a bit of an introduction. PhD at Hiroshima University, current position as SLAC Senior Staff Scientist, leading the SLAC JAM4 team. He's been involved in detector simulation for 40 years, one of the original developers of JAM4. I have fond memories of us working together 20 plus years ago when Babar was one of the early adopters of JAM4. In JAM4, he served 10 years as deputy spokesperson, followed by another 10 as spokesperson. He's taught more than 3,000 users in the US and over the world JAM4 tutorial courses. So there's nobody better qualified to talk about his personal view, with the emphasis on personal, entirely unofficial view of JAM4 in 2030. So with that, Makoto, please go ahead and don't rush too much. I hope everybody can stay.
Okay, thank you. So do you see my screen?
Yes.
Okay, thank you. Okay, yes. Oops. Okay. And thank you for the, thank you for the organizers to speak my personal view. And here the preamble. We understand JAM4 will likely remain as the main detector simulation engine for high energy nuclear physics in 2030s. So, as Tor said, let me try to present my personal view on how JAM4 would or should evolve in coming 10 years to meet the requirement of the 2030s. But let me repeat again, this is my personal view. And in this presentation, I'm not representing any institution or collaboration. And also, I will not take any responsibility on ensuring this evolution to happen unless I'm paid for. So here's the content. And let me repeat once again of the short introduction of who I am. Some of the younger people don't know, may not know me. So, and some histories of how JAM4 has been involved. And also how JAM4 works as a detector simulation engine. And a bit of my personal thought on how GPU should be integrated into the simulations, and how JAM4 should evolve in the coming 10 years. So let me start with who I am. So when I was undergrad, I was actually a material scientist and working for ion implantation simulation. Then as a graduate student, I joined the NA23 of CERN and worked with the original JAM developers so that I could learn how to read Fortran code written in French, Then, after I got PhD, I joined solenoidal detector collaborations at Super Collider. And I was in the detector simulation group. And I also had some early discussions on how JAM4 should evolve, that time from JAM3 to 4. Then I joined when we launched the JAM4 R&D. I joined, not because of my knowledge on object orientation or C++, but my long history along with JAM4. And I note here that sudden death of Super Collider and postponement of LHC gave us time for JAM4 R&D. So then I joined also to the Atlas, and I'm one of the launchers of this chaos project. The acronym is Compromised Heterogeneous Atlas Object-Oriented Simulator, but officially it's not that way, but it's Comprehensive Atlas of Object-Oriented Simulator anyway. Then I moved to SLAC Then I took role of the deputy spokesperson for 10 years, and then the spokesperson for another 10 years, and I'm now here. So here's a brief history of GEAN4. And we started early discussions, for example, at CHEP, there are several presentations. Then we officially started the R&D phase in December 94 for 4 years as planned, and we released the first public release of GEAN4 version 1 at the end of the 98. Since then, in past 20 years, we had GEAN4 had several major architecture or design revisions that includes, for example, the first big one was migration to STL, then cut per region requested mainly by Babar, then parallel world that I'm going to discuss later, then multi-threading. And current version of GEAN4 is version 10.7 patch 2 release. Patch 2, that was its current version. And we are going to make a major release at the end of this year, December the 10th. That will be GEAN4 version 11. That includes the introduction of the task-based parallelism. So here, let me summarize how GEAN4 is widely adopted. Because of course, the biggest reason is wide coverage of accurate physics models, powerful geometry package, nice GUI and visualization options, they all are provided. And also GEAN4 is a toolkit so that it was easily adapted or wrapped into the user's framework. But also the key things here, the stability of the major APIs is an important aspect, I believe. So new architectures were encapsulated nicely and mostly invisible to the user. For example, when GEAN4 introduced multi-threading, migration of the user's code was extremely simple and easy and straightforward, except of course, the making their own user's code itself thread safe. And also, I must note here that stability of the major APIs also incubates new development and contributions, new physics model, for example, new geometry module, new GUI and BIS drivers, and so on and so forth. So most cases, new functionality based on new architecture comes with additional APIs rather than changing the API. And GEAN4 is not a turnkey application, and should not be a turnkey application in 2030s. So that the user must build an application on top of GEAN4. Here, I just suggest a small thing that we should not create too many layers of thick wrappers. It's better having a single thin wrapper for the sake of quick catching up of the new interfaces. So here's very simplified schematic diagram of how GEAN4 simulates the detector. At the initialization, somehow we take geometry and calculate cross sections. Then we get into run. That is basically event loop. At each event, we read primary event from Monte Carlo generators and put particle into stack. Then from stack, each track is popped out and tracked. Track experience several steps. And at each step, it does physics calculation and field integration and navigation over the volumes. And if necessary, step makes a hit at the detector. And once step being over, it comes back with secondaries, and secondaries are pushed back to the stack. Okay, that is the key scenario. And once the event is over, so it repeats for all the particles in the stack, and then if the stack becomes empty, it goes to the next event, and then next event, every event is over, then run is over, and spit out the detector hits, Monte Carlo truths, and histograms, and so on and so forth. So, since the very beginning of GEAN4 ran in a sequential mode. That means single core does everything. So we have main, RAM, event, tracking, and stepping. That was simple. Then, since Jan4 version 10 in December 2013, we introduced multi-threaded event level parallelism. That takes the advantage of the independence of each event, so that many cores or thread, if you like, processes events in parallel. And geometry cross-section tables are shared over the thread. So here in a MT mode, cross-sections or detector geometry, they are stable so that they are shared by all the cores or all the threads, while the transient data like track, hits, are the thread local. And so here the master thread, and for each worker thread, we have local run manager, event manager, tracking manager, stepping manager to do the simulation. So we have nice, beautiful linearity. And for example, we have successfully run in combining MT and MPI on mirror blue genes with all of its 3 million threads with full CMS geometry and field, and demonstrated that the spare time of mirror was actually enough to cover all the run to LHC simulation needs. But also, we understood that I/O is a limiting factor to scale large concurrent threads, granular input data files or output data, histograms, etc. Anyway, so now from the new release of this December, Jan4 moved to task-based event level parallelism. That means that we decouple a task that, in other words, event loop from a thread, so that the user can have more flexible load balancing. Here, the worker thread and task are basically spread independent, so you can create as many tasks as you need and put the task to the worker thread. Okay. And in the coming years, we move toward task-based sub-event parallelism. And we split events into sub-events and task each sub-event to the worker thread. Here, the sub-event could be subgroup of primary tracks. For example, for the case of Alice, they have huge number of primary tracks. Okay, but more importantly, the sub-event can be group of tracks getting into a particular detector component. Okay. Right, for example, calorimeter or dark or scintillator or Cherenkov kind of things. And it's quite suitable for heterogeneous hybrid software hardware. So here, we have sub-event here. And sub-event, for example, if it is sub-event for calorimeter, it may go to the worker thread that is dedicated for calorimeter simulation and so on and so forth. So on hybrid computing, it's my personal view what GPU should do. There are two different usages of GPU. One is full Monte Carlo detector simulation. The other is the fast simulation. And for the Monte Carlo simulation on GPU, we have already, I believe it's hopeless to port the entire Jan4 to a single process on GPU. So I believe each GPU process should have very limited scope in physics coverage, particle type, geometry, and material, and so on and so forth. For example, optical photon transport is the ideal case, and EM shown in calorimeter without backsplash or punch through could be a good sample. And a task on GPU should behave like a black hole. I mean, the darker a task is, the better performance it has. And darker means the less output. Okay. So I believe from GPU side, step or track should not be taken out. And reshuffling tracks over tasks is the worst thing to do. Okay, and we have to minimize the task, minimize the step or track information out from the from GPU. Transferring output is a serious bottleneck. Okay. By the way, just a side note that this coming version of Jant 4.11, it will include a new first version of the G4 HEP EN module. That is a complete set of EM physics specialized and optimized for HE NP calorimeter potentially ported to GPU. Okay. So let me come back to this picture. Okay, so here, once track is done, processed, several secondary tracks are pushed back to the stack. So if we put a task to, for example, to a GPU of this part, here must be the bottleneck. So what we are going to do is here. We create basically two separate stacks. One is inside master, and the other is in the worker. And we just put parent tracks into the task sub-event. Then within the sub-event task, the local stack takes care of all the secondaries. Okay. With this, the sub-event task will fit well to GPU, for example, optical photon transport or EM shower. Okay. So with different color goes to different thread. Now, in the fast simulation, and classical fast simulation such as GFlash or more modern fast simulation powered by AI, they all are very useful. And parameter optimization is ideal usage of GPU. And parameters must be optimized, tuned for every detector, so that we need to start training as soon as detector hardware is fixed, or even earlier, as Cristiano mentioned. And we need careful consideration of outgoing tracks. Backsplash or punch-through track will be the bottleneck for sure. I'm not saying that GPU, for example, Calgan, cannot generate punch-through or backsplash, but the thing is, if you send such backsplash particles back to the main stack, here for sure is the bottleneck. And also, I have to say that fast simulation must not be applied to detailed geometry. More than a decade ago, we had a lesson that CMS successfully employed GFlash on its crystal calorimeter, while Atlas couldn't use in efficient way on its accordion calorimeter. Okay. So here, Jant 4 has a functionality to allow more than one geometry description in parallel that we call layered mass geometry. So in the mass world, you anyway have to implement everything. All volumes should have its own, every volume should have its own material. But in parallel world, you can define very limited part of the geometry with material and overlay like this. Okay. And when track comes to this part, for example, it will see red material rather than blue. Okay. So it's an alternative way of implementing a complicated geometry by Boolean operation. But also, more importantly, such parallel world may be associated to some selected type of particles. Okay. So you may define the geometries of different level of details for different particle types. For example, for electron, positron, gamma, you see the averaged crude geometry, while more important particles such as muon, you implement full detailed geometry. Okay. So that shower parameterization, such as GFlash, may have its own specified simplified geometry. That will help a lot of the performance. So Here's the simulation challenges toward 2030s. We understand the simulation throughput need to be faster by order of 10 to even 100, and contribution of simulation to contribute the simulation to maintain the systematic uncertainty very low. And also new detector hardware, for example, high granular calorimeter, will cause the higher demand of the computing of simulation. So strategies, I believe, are the following. We should do the detailed simulation as much as possible on CPU when sustainable or when no alternative, but with nice, clever creativity such as stack management, layer mass geometry, event biasing, and so on and so forth. And on GPU, we should combine variety of single-purpose optimized GPU tasks. And we have to be careful to minimize the output from each task. And concerning about the fast simulation, we have to employ them as much as needed and on CPU, but parameters should be optimized by GPU. And more modern AI-based fast simulation could be employed. So let me just introduce you of an activity I'm involved in currently that we call EAST, EA simulation tool. And EAST is a turnkey application as well as a toolkit for electron ion collider simulation studies built on top of Janfo. And here are the requirements, a lot of flexibilities, but importantly, we plan to make this wrapper as thin as possible to directly use the native Janfo functionalities as much as possible for timely catch-up of Janfo evolutions and leverage the new and rapidly evolving computing architectures. So it's a strong tie-up of the AIC user community, EAST developer team, and Janfo core developers. And we already have some nice sample geometry and run on EAST that includes both H and Athena detectors. So to sum up, again, this is a very personal view. And I believe Janfo will likely remain as the main detector simulation engine for the high energy nuclear physics experiment in 2030s. And also for training the machine learning, the AI as well. And there are plenty of opportunities in GPU-based detector simulation, both in full Monte Carlo and fast simulations. And I believe each GPU process should have limited scope, and each GPU process should have minimal output to get the best performance. And Janfo is making steady steps toward to meet the requirements as the simulation engine that runs on heterogeneous computing architecture. That is all I have. Thanks a lot.
That was excellent, Makoto. Thank you very much, and very time efficient. You caught us up lots of time. So in the absence of hands, yeah, let me ask about slide 21. I really like this sub-event task with its own stack. You mentioned that it's amenable to optical photon transport, EM shower, and calorimeter approaches to use GPU. So our efforts in those directions, like optics
Yes,
and polarities,
definitely,
they're using that approach?
Yes. Oops. Sorry, can you hear me?
Yeah.
Oh, okay. Yes, we are going that direction. And also, I couldn't mention about this part, that sub-event task may take tracks of more than one event if necessary to populate the task, so that we need sorter or merger. Okay.
Mm-hmm.
For example, one particular task may have tracks from more than one event, so we need merger, or sorter and merger. Sorry.
Okay, thanks.
And sorry, so let me add here that there are several stacks here. So one stack may stack up optical photons, while other stack stacks up, particles that may go for EM calorimeter. The thing is, we should not get track back to from this side to that side.
Yeah. Very nice. Thanks. Okay, not seeing hands, I have another question. How do you think people should be defining their geometries in 2030?
Very good question. Of course, GDML or CAD, if you like, is one way to go. In particular, to import the structures, support structure kind of things. But level of detail is the big concern for our simulation. And if we ask CAD engineers to draw a picture, they always come with the most detail possible geometry. And there's no easy way to simplify it. So that part, we may still need to come with some C++ code maybe, or I don't know.
Yeah, okay. That's one of my pet peeves with Jam4 at the very beginning, that it was it was defined as outside the scope, how you actually define your geometry.
Once screw and nut are implemented inside CAD geometry, it's not easy from Jam4 or GDML side to get rid of them.
Yeah. Okay, are there questions? Are there questions written down looking? No. So no hands? 2 hours has been enough for people. Probably.
Maybe they're hungry.
Yes, I know you are.
Yes, I am.
Okay, I'll ask the provocative
Yeah,
question.
one hands.
You think you're going to hit the 100 times speed up target for complex geometries? It's a heck of a goal.
Yeah, 100 is if you blindly or naively do every detailed simulation, you may not. But for example, the where the slide? No. Here, stack management to get rid of some events that are not interesting at the very earliest stage, or layer mass geometry to let electron positron gamma in calorimeter not seeing the details, or event biasing, or this kind of clever creativity, I must say. I believe we can meet 100.
Okay, thanks. That was helpful.
Okay, then we can bring it in at 2 hours. Thank you very much to everybody for hanging in there. We had 3 extremely rich, excellent talks that I think really were worth the investment of our time. So thank you very much to the speakers. And thanks, everybody. So long, go eat.
Okay, thank you so much.
Thanks, everyone.